Welcome to the third part on synchronous machines. Here we start by discussing what finite state machines are. The functionality of a synchronous circuit in its canonic form is so important that it justifies a term which is called finite state machines. Let's define what a finite state machine is. It is a six-tuple A that consists of Q, sigma, delta, lowercase delta, lambda, Q0. Let's explain what each of these components signify. Q is a set of states. Big sigma is an alphabet of the input. Big delta is an alphabet of the output. Lower delta is a function from pairs, ordered pairs of states and inputs to states. This function is called the transition function. Lambda is also a function from pairs of states and an input, but the range is a symbol in the output and is therefore called the output function. Q0 is the initial state. So let's explain how such a machine A performs a computation. So, a finite state machine is an abstract machine that operates as follows. We have an input sequence, x0, x1, and so on, where each xi is an element called a symbol over the input alphabet sigma, big sigma. The output is a sequence, yi, where I goes from 0 to n minus 1, of symbols over the alphabet big delta. The finite state machine transitions through a sequence of states, Q0, Q1, Q2, up to Qn, as it is fed by this sequence of inputs. The state Qi in this sequence is defined recursively. Q0 is part of the specification of the finite state machine. It is the initial state. Qi plus 1 is defined to be delta, the transition function, applied to the state Qi and the input xi. And the output yi is the function lambda, applied to the state Qi and the input xi. So one way to think about what a finite state machine does is as follows. I begin in some state. I like to mark this state with two circles, and my initial state is Q0. Now I get some input, I denote it by x0, and that input causes a transition, because I'm in state Q0 with input x0, causes a transition to a state called Q1. As I receive the input x0 and I'm in state Q0, I output y0. So I write here y0. Now when I'm in Q1, I get the input x1. The transition function tells me that I have to go to state Q2, and I output the value y2, and so on. This is the way the computation proceeds. Now it is important to understand that these QIs need not be distinct. So it might be the case that after having received a certain number of inputs, I return to a state which I have already visited. Okay? That's the first thing I want to emphasize. The second thing I want to emphasize, that when I'm in a state, say Qi, it is possible that I will get any one of the input symbols from the alphabet sigma. Let's say sigma contains 3 different symbols. So I might have 3 different transitions emanating out of Qi, depending on whether my input is, say, sigma 0, sigma 1, or sigma 2, where my input alphabet is sigma 0, sigma 1, and sigma 2. So for each symbol in my input alphabet, I may have a different transition that takes me to a different state from the current state. Okay? We'll elaborate on this shortly. When we talk about finite state machines, it depends on the field. Sometimes they're called finite automatons with outputs or transducers. In the literature, there's a distinction between Mealy machines and Moore machines. What I described as a Mealy machine. A Moore machine is a finite state machine in which the domain of the output function is the current state, and the output does not depend on the current input. So in that case, lambda is just a function from Q to big delta. Okay. One way to depict finite state machines is to use state diagrams. I actually showed you what a state diagram is a second ago, but let's define it formally. A state diagram that corresponds to a finite state machine A is a directed graph G, whose set of vertices is the set of states of the finite state machine A, and the set of directed edges E is given labels x comma y, where x is a symbol in the input alphabet and y is a symbol in the output alphabet. The edge set of the directed graph G, which is the state diagram that corresponds to A, this edge set is defined to be all the ordered pairs q comma delta of q comma x. Q is the current state, x is the input symbol, and given a state q and an input symbol x, delta tells us what is our next state. Okay, so the edge emanates from q and enters the state which is delta of q comma x. We label this edge by the pair x because the first coordinate tells us what is the input symbol that was given to us when we were in the state x, in the state q, and the second symbol is the output symbol that we output when we're in the state q and we're fed with the input x. The vertex q0 that corresponds to the initial state of the finite state machine is usually marked in an FSM by a double circle. Now we remark that the state diagram is in fact a multigraph because one may allow more than one directed edge between two vertices. This is the case in which two different input symbols create the same transition. Such edges are often called parallel edges. We note that the out degree of every vertex in the state diagram equals the cardinality of the input alphabet. This is a mistake. Good. Okay, so let's see an example of a finite state machine that has two states. This is the first state, Q0. This is the second state, Q1. So our set of states consists of Q0 and Q1. Our alphabet in this example consists of simple bits, 0 or 1. This refers both to the input alphabet and to the output alphabet. They're both a single bit. The transition function and the output function are depicted by the state diagram. So in state Q0, if my input is 0, I transition to state Q1 and output 1. In state Q0, if my input is 1, I output 0 and stay in the same state. This is why I have here the self loop. In state Q1, if the input is 0, I output 1 and stay in Q1. If the input is 1, I transition back to Q0 and I output a 1. Okay, so this state diagram gives me a full specification of the finite state machine. It tells me what the set of states is, what the set of inputs are, the set of symbols of outputs, the transition function, the output function, and the initial state. Okay, there are two tasks that are often associated with synchronous circuits. These tasks are defined as follows: analysis and synthesis. Analysis means that I give you a synchronous circuit and you want to describe the circuit using a finite state machine. So I go from C to some automaton A. Okay, so this is a synchronous circuit, and this is a finite state machine. And this direction, let's call it analysis. The other direction, in which I give you a finite state machine and I ask you to implement this finite state machine using a synchronous circuit is called synthesis. Okay, let's explain how analysis is performed. Okay, so we're given a synchronous circuit and we want to model this synchronous circuit using a finite state machine. So this task of analysis proceeds as follows. We need to define the set of states, the alphabet of the inputs, the alphabet of the outputs, the transition function, the output function, and the initial state. Okay, so we define the set of states Q to be 0, 1 to the power of k, where k equals the number of flip-flops in our circuit C, in the synchronous circuit C. This is the set of states. So the set of states tells us actually what are the outputs of the flip-flops. There are k flip-flops, so we can represent the outputs of the flip-flops using k bits. The initial state Q0 is the binary string of length k that equals the initial outputs of the flip-flops. So here I'm assuming that the flip-flops have initial values, that there's a reset signal that tells me what the initial values of the flip-flops are going to be. Let's say all zeros. The input alphabet, capital sigma, is 0, 1 to the power of L. These are binary strings of length L, where L denotes the number of input gates in C. So C has L inputs. In each clock cycle, we feed C with L bits through the input gates. Capital delta is the set of all binary strings of length R, where R denotes the number of output gates in C. So in each clock cycle, C outputs R bits. Now we need to define the transition function and the output function. The transition function is a function from pairs of strings of length k and strings of length L to strings of length k. So this string encodes the state. This string encodes the inputs. And this string encodes the new state. So this is the function which is implemented by the combinational part of the synchronous circuit. We have a state, we have an input, and we have the next state. The next state is going to be the state in the next clock cycle. The output function also is applied to the state and to the input, but it gives us the values of the outputs. Okay? So this function delta and this function lambda are exactly the same functions that we saw in the canonic description of synchronous circuits. Let's see the canonic description. Yeah. So these are exactly these functions, lambda and delta. Delta tells us what's going to be the next state as a function of the current state and the inputs, and lambda tells us the value of the output as a function of the current state and the inputs. It's exactly the same thing. So this is the task of analysis. Let's see a few examples in which we could apply analysis. We start with a counter. A counter of n bits is defined as follows. It basically doesn't have any input except for the clock signal. It has an output n that consists of lowercase n bits. And there's no input. The input is implied. It is the missing reset signal, which doesn't appear here. We don't need it because we assume that the flip-flops are initialized to all zeros in the clock cycle 0. Now the functionality of the counter is that the output n in clock cycle t represents in binary the value of the current clock cycle mod 2 to the power of n. This is our functionality. The implementation is quite trivial. We use an incrementer. We already saw what an incrementer is. Let me remind you. An incrementer is nothing but an adder, a binary adder, in which you have your input here, the same input here. This is our in, this is our in. And here the second input, you could think of it as representing the number 1, and the carry in is a 0. Okay, so it just adds a +1. We don't connect the carry out. This is the carry out. We don't care about it. We only look at the n bits of the sum. So this is what an incrementer does. It takes n, it adds to it a 1, carry in is 0, and this is the sum output, and we ignore the carry out output. We take these n bits, we feed them to a register of width n, controlled by our clock, and this is the output of the Q. Okay, so we claim that this is a correct circuit. Let's see why. We need to prove it by induction. What is N0? Well, N0 is 0 because we assume that the flip-flop is initialized to all zeros. Okay, so this would be the induction basis. The induction step, the induction hypothesis, would be that n of t equals t mod 2 to the n. And now let's do the step. We know that d at time t equals n at time t plus 1 mod 2 to the n. And we know that n at time t plus 1 equals d at time t. And this, by the induction hypothesis, equals t plus 1 mod n. Right? Very good. I want to emphasize this part holds because of the functionality of the incrementer, and this part holds because of the induction hypothesis applied to n of t. Very good. So this completes the correctness of this implementation. Now we could try to analyze our counter. In aftermath, we could ask, what is the finite state machine that corresponds to this synchronous circuit? We know what the synchronous circuit does. We designed it so that it implements a counter. But let's try to see what the analysis gives us for this circuit. And we will use a counter with 2 bits. So the counter has 2 bits, namely the 2 flip-flops in the counter output 2 bits. These 2 bits could be 0, 0, 0, 1, 1, 0, and 1, 1. These are our 4 states, the possible outputs of the flip-flops of the counter. Now, the transition, we don't have an input. The transition is what the incrementer does, right? So if we have the state 0, 0, we transition to the state 0, 1 because the counter increments. Because the counter performs an increment over here. So if we had state 0, 0, the next state is going to be 0, 1. And the state after that is going to be 1, 0. And the state after that is 1, 1. And then the increment overflows and outputs a 0, 0. So this is the transition between the states. Now the output here in this circuit is simply the state itself. So I didn't write it on the diagram, not to clutter it. Okay? We could also consider a counter with inputs. So here we have a counter with a single input, 1 bit, and the same type of output as before. But here the functionality that we're interested in is in counting the number of times in which x equals 1 throughout the history. So we're summing for all clock cycles, from clock cycle 0 to clock cycle t, whether xi was 1 or not. If it was 1, we add these numbers and take mod 2 to the n. This is what we want n of t to represent in binary representation. Okay. So instead of just counting 1 by 1 in every clock cycle, we count only if x equals 1. So here's a suggestion for an implementation. We take the current state and we either keep it or we increment it based on the value of x. So if x is 0, we keep it. If x is 1, we perform an increment and get the next state. I'll leave it as an exercise to prove that this circuit is indeed correct. But let's focus, before we leave it as it is, let's focus on the induction basis of this proof. What happens when I equals 0? Well, when I equals 0, assuming that the flip-flops are initialized to all zeros, then the output here is all zeros. But it might be the case that x0 is 1, in which case n represents the number of 0 and the right-hand side equals 1. So the circuit is wrong. So this means that this is not the right place to read n. Where is the right place to read n? I'll leave it as an exercise. One, fix the circuit, it's wrong. And two, prove the correctness. Prove correctness after fixing it. Let's analyze the circuit we have after it was fixed. Well, it has 4 states that correspond to the possible outputs of the flip-flops: 0, 0, 0, 1, 1, 0, 1, 1, which correspond to 0 mod 4, 1 mod 4, 2 mod 4, 3 mod 4. And instead of outputting the state, let's output yes if the value of the counter is 0 mod 4, and let's output no if it's not. So here I'm looking at a modified FSM in which the output alphabet consists of yes and no. And you see that if I'm in the 0 state and I get an input which is 0, then it is divisible by 4. If I get an input that equals 1, then it's not divisible by 4. And I transition to the case which corresponds to the residue of 1. And if I get a 1, I transition to the state which corresponds to a residue of 2. I get another 1, I transition to the state that corresponds to a residue of 3, and then back to 0. Now notice that here I output a yes, here I output no, no, no. In these cases the input is a 0, so I stay in the same state with a no. In this case the input is a 0, I stay in the same state with the output being yes, because the residue is 0 mod 4. Let's go back to our sequential adder and analyze it. This is the case in which our sequential adder has a reset. This is my initial state. In my initial state, if my 2 bits a plus b are less than or equal to 1, the carry out is 0, and therefore I stay in this state, and I output the XOR of a and b. If a plus b is 2, I output a 0, the carry out is 1, so I transition to this state. Now when I'm in this state, I need to consider 2 cases. Either there is a reset or there's no reset. If there's no reset, the carry out is 1 if and only if a plus b is greater than or equal to 1, because the carry in is 1. And the output is 1 XOR a XOR b, because the carry in is 1. If there is a reset, then I pretend that this is actually my state. And now the transition is, if a plus b equals 2, I actually do this transition. And if there is a reset and a plus b is less than or equal to 1, then I'm pretending that I'm here and I do this transition. And this is what you see over here. These 2 transitions apply to the case in which there's no reset, and I'll leave it as an exercise to think about them. Let's revisit shift registers. This was the definition of a shift register with n stages. Recall that q of n minus 1 at clock cycle t plus n equals the input d0 in clock cycle t. So you delay the input by n clock cycles. We propose the following implementation of the shift register. It's just a cascade of full adders. We saw this design. And now we want to perform an analysis. Let's perform an analysis for the case that n equals 2. N equals 2, we have two flip-flops. Their outputs are 0, 0, 0, 1, 1, 0, or 1, 1. And now, depending on my input, I perform the following transitions. In 0, 0, if the input is 0, I stay in the same state, and I output 0. In 0, 0, if the input is 1, I output a 0. This would be this 0. And I move to this state because I pushed a 1 from the right. If I'm in this state and I push a 1 from the, and I get an input which is a 1, so I push a 1 and I get to the state 1, 1, and I output this 0. This is the output that you see over here. Now if I push a 1 again, then I am in a self loop, because this one is output and this one is input, and it becomes this one. Now if I input a 0, then my next state will be 1, 0. This 0 is the 0 that I input. This one is this 1 which I output. And now I'm in this state, and so on and so forth. This graph has a very special name. It's a de Boyne graph. And you can define this de Boyne graph for every n. Here it is for the case that n equals 2. It's a very interesting graph. Okay, let's revisit RAMs. This was the specification of a RAM, and I want to depict its finite state machine. This is not the full finite state machine of a RAM of 2 bits. And what you see here is that the finite state machine is incredibly complicated, and it's not an effective way to describe the RAM. Okay, the RAM has 2 to the n states, and where n is the width of our memory, too many states, and we cannot follow it. Yeah. So if our address space is n bits, then we will have 2 to the n different states, and this becomes a complete disaster, not effective. Yes, I want to emphasize. Here I have n. It's not 2 to the n states, it's 2 to the n. Let me explain why. When n, I have here n bits in the memory. So I have n flip-flops, n bits of address, sorry. That means that I have 2 to the n different flip-flops, and that means that the number of states is 2 to the power of 2 to the n. Okay, so it's not 2 to the n, it's 2 to the power of 2 to the n. Sorry for the mistake I said before. And as you can see, even for very small values of n, the number of states is way too big, and therefore this way of trying to explain the functionality of a RAM by a finite state machine is highly inefficient. Let's summarize. Before we summarize, I want to analyze the effect of adding initialization to a synchronous circuit. So I have here a synchronous circuit C that doesn't have an initialization signal. It works based on the assumption that the flip-flops magically output a specific value, say all zeros, in clock cycle 0. Now we take our circuit C and we introduce initialization through a reset signal that initializes the output of all the flip-flops, as we saw before, using a mux that, in case the reset is 1, selects some predefined initial value. Okay? Good. So we have these muxes, which are controlled by the reset. and they select either the output of the flip-flop or the initial state that the reset tells us that we want to select. So we start with a circuit C, and we transformed it to a circuit C prime, which has a reset. So the circuit C worked under an assumption that the output of the flip-flop, say, was all zeros in clock cycle 0, and the circuit C prime does not need this assumption because it uses a reset signal to select zeros whenever the reset is 1. Sorry, let's not denote it by C prime, by C hat. So C hat is our new synchronous circuit with the reset signal. And now what we do is we perform analysis to C. We analyze it. And we call the finite state machine, which corresponds to C, we call it A. So this is an FSM. We could also analyze C hat, and we will have our finite state machine A hat, which corresponds to C hat. So this would be a separate analysis. Now you may ask, what is the transformation that describes the mapping between A and A hat, where A is the finite state machine that models C, and A hat is the finite state machine that models C hat. Okay? So now we want to focus on this blue mapping. Good. So this is A, the 6 tuple, and this is A hat, the 6 tuple, with the primes. And we want to see the relation between Q prime and Q and so on. Okay. So same set of flip-flops. So we did not change the set of states, right? So it is 0, 1 to the power of the number of flip-flops, right? No change. Here in Q, in A, we assume the initial state to be Q0, say the all zero string, and here the initial state in A hat, well, you could assume that it is the same state as it is in Q0. It doesn't really matter because you have a reset signal, but it's just convenient to assume that this is the same initial state. Now, the input alphabet in A hat consists of the input alphabet in A plus an extra bit. This is the reset signal, which is either a 0 or a 1. The output alphabet is the same alphabet, there's no change. The transition function. Okay, so the transition function is a function of the state and the symbol in the input alphabet. Now the symbol in the input alphabet will consist of a symbol in sigma plus the value of the reset signal. So delta prime is defined as follows. Either the reset is 0 or the reset is 1. If the reset is 0, then delta prime of Q, comma, sigma, comma, 0 is just delta of Q, comma, sigma. You do the same transition as in A as you did before because the reset is 0. If the reset is 1, then in effect you have an immediate transition to Q0, and now you do what A does if it were in Q0 and you had the same input sigma. So delta prime of Q, comma, sigma, comma, 1 is delta of Q0, comma, sigma. This is if the reset is 1. What about the output, lambda prime? If the reset is 0, the output is the same as it is in the machine A. There's no difference. But if the reset is 1, then we pretend that we are in the state Q0 with the input sigma, and our output will be as if we were in state Q sigma. So you can think of it as we do an instantaneous transition from whatever state we're in into state Q0, and then we work on from that point. Okay? Now let's talk a little bit about synthesis. Synthesis is a process in which we have a finite state machine and we want to find a synchronous circuit that implements this finite state machine. So we're given a finite state machine and our goal is to find a synchronous circuit that implements the finite state machine A. How do we do this? Well, we look at the set of states, we look at the input alphabet, we look at the output alphabet, and we have to decide how to encode each one of these sets using binary strings. So we look for functions f, g, and h, where f is a function from q to k-bit strings, sigma is a function from, g is a function from capital sigma to l-bit strings, and h is a function from capital delta to r-bit strings. Now, in general, we would like these functions to be one-to-one, so that each string is used to encode at most one state, at most one input symbol, or at most one output symbol. Now we want to do is to implement a combinational circuit that implements our transition function. The transition function, recall, is a function that accepts a state and an input symbol. So now we will have a Boolean function that receives a k-bit string, which represents a state, an l-bit string that represents an input symbol, and gives us a k-bit string that represents the state that we transition to. Now notice that these functions f and g are not necessarily onto. If they are not onto, then this function b of delta is actually a partial function because we only care about the k-bit strings that actually encode a state and the l-bit strings that actually encode an input symbol. Okay? Now we want this function to satisfy the following. If I give you an encoding of a state and an encoding of an input symbol, then my transition is to a new state, which is encoded by f of the new state I need to move to, the state delta, when I'm in state x and my input is y. Similarly, I need to design a combinational circuit, C lambda, that implements the Boolean function that is given an encoding of the state, an encoding of the input, and gives me an encoding of the output. So, given an encoding of the input and an encoding of the state, and an encoding of the output, I want to get an encoding of the state and an encoding of the input. I want to get an encoding of the output that corresponds to the output when I'm in the same state x and I get the input z. How many flip-flops do I need in my implementation? Well, I need k flip-flops. I want this function to be one-to-one, so k better be at least as big as log base 2 of q. Otherwise, this function has no chance of being one-to-one. Now, it's not clear that minimizing k is the greatest idea. Sometimes it's a good idea, sometimes it's not such a good idea. Certain encodings lead to more complicated Boolean functions b delta and b lambda. Okay, so the question of selecting the right encoding is a very complicated task, and there's no simple solution to this problem. So all I can suggest is the brute force method, in which I just pick k, l, and r to be large enough so that these functions are one-to-one. I choose some arbitrary functions which are one-to-one from q, sigma, and delta. Then I get my definition of my transition function. This is a Boolean function or a partial Boolean function, which I know how to implement using a combinational circuit one way or another. I do the same for b lambda, and that is how I do synthesis, and I cannot offer any real optimization for this purpose. There are lots and lots of heuristics, tricks that work in general, but we cannot prove anything about them or say anything significant about them, because the problem of choosing these encodings and implementing these functions are complicated problems that we do not have general algorithms for solving these problems. Okay, let's go back to our finite state machine over two states, and let's perform a task of synthesis. Namely, we want to design a synchronous circuit that implements this finite state machine. So in this finite state machine, our set of states consists of two states, Q0 and Q1. Our input alphabet and our output alphabets are already bits. So the encoding that we will choose for them will be the trivial identity encoding. Good. So I need to encode states using a bit. I need to encode input symbols using bits, output symbols using bits. I think it's more instructive to think of it as 0, 1. And I'll use the natural function where Q0 is mapped to 0 and Q1 is mapped to 1. And G and H are just the identity functions. Now, I ask myself, what are these transition functions? What is the transition function that is induced by this finite state machine? So I give you a state, and I give you an input symbol, and ask you what is the new state, right? So let's go back to our state diagram. So when I'm in state 0, and the input is 0, I go to 1. So you see here that 0, 0 goes to 1. And when I'm in state 0, and the input is 1, then I go to 0. So the transition from 0, 1 is back to 0. So this 0, 1 is back to 0. So now all I need to do is implement this function. I notice immediately that this function is simply not of the second coordinate, right? So it's not of gy. I could do the same thing with the output function, fill the truth table, and notice that the truth table tells me that the output is 0 if and only if f is 0 and g is 1. So it follows that b lambda of fg is f of x or not g of y. Good. So I have an implementation both for the transition function and for the output function, and therefore this would be the synthesis. Have a single flip-flop, which outputs are my state, which is either a 0 or a 1. I have my input, which is a single bit, which is either a 0 or 1, and I have my circuit for computing the output, my circuit for computing the next state, which I feed into the flip-flop, and this would be an implementation of a finite state machine using a synchronous circuit. Let's summarize what we saw in this part. We defined synchronous circuits. We showed that their functionality is well defined via a simulation algorithm. We presented synchronous circuits in canonic form. We discussed initialization and reset. We saw that the functionality of synchronous circuits can be modeled by finite state machines and state diagrams. We performed analysis and synthesis of synchronous circuits. And of course, we noticed that FSMs are not useful to model synchronous circuits that have many flip-flops, because the number of states is exponential in the number of flip-flops. Thank you very much.